Alright, this class is going to be about heat and temperature, and I'm going to show you the difference between those two terms that hopefully by the end of the video you're going to have a very clear understanding of them. Alright, so let's start with a definition. Heat is the energy that causes a temperature change. We can start with that definition and we can build up on it. Well, most of the times that's going to be the definition. This is going to change, for example, when you add energy to a substance and it's going to change into another phase. For example, when you change liquid water into vapor state, into vapor, if you change it into the gaseous state, you're going to need some more energy to make that phase change, but we'll talk about that later. Let's hold with this idea that energy changes temperature. That's what causes temperature and a change in temperature, of course. And well, what do we have here? For example, we have a pan and it's on an oven, but let's imagine that it's off. We turn off the oven and the pan, inside of it there's a substance. Let's say that it's a small amount of water and it's 24 degrees Celsius, a cool 24 degrees Celsius ambient temperature um, amount of water. And the energy that I'm going to be using, as you can see here, it says Q equals 0 joules. And this Q is going to be the letter that we will be using, or the symbol that we will be using for representing energy. So we have 0 joules. And this J is going to be the unit for energy, as we have seen before. That's going to be the energy unit for heat as well. So we have 0 joules. And then later on, I'm going to turn on the oven. We got energy. Now we got 10 joules. Now when you add energy to this pot, the water inside of it, it's going to change its temperature. Let's imagine that with this amount of energy, the temperature changed to 40 degrees Celsius. It changed to this, so that's the final temperature. The question is, by how much did it change? What was the change in temperature? That's going to be also something very important that we will be seeing here. The change of temperature was 16 degrees Celsius. Remember that little symbol that we got there, the triangle one? That is the delta symbol. And it means change. So there's a change in temperature. It went from 24 to 40 degrees Celsius. There's a change. And how do you get a change in mathematics? Well, we got to use a subtraction. That's why the formula for change of temperature is going to be TF minus TI. The final temperature minus the initial temperature. That is going to tell us the change of the temperature. Okay, so this symbol delta means that this other one, this variable, it's going to be changing. Doesn't mean that you have delta times a number. It's not a number, delta. It just states that this guy is going to be changing. Okay, so how much energy is required depends on what you want to heat up. For example, if you want to heat up something that is bigger, for example, it depends on the mass, okay? So it depends on mass, substance, the type of substance, and the delta T. So we gotta find a way to uh, get the property of how much heat a given substance needs. I want to tell you what that property is. And we also need to know how much temperature change you want to get in order to use a given amount of energy. So the idea that I want to convey right now is that the amount of mass is going to tell you how much energy you require. For example, it's not the same to heat up a coffee cup like here than using one of those uh, bigger containers with water. I mean, right, you don't, if you use a huge pot like this one and you fill it up with water, you're gonna need more energy to heat up this pot, huge pot, than this small coffee cup. Okay, so you need to know how much mass you have in order to know how much energy you require. And of course, we need to get the substance. Now, to understand this, let's imagine that it's a hot day and you're getting back from wherever and you're going back to your car. You left your car in the parking lot and you want to go back to your car, and it's a hot day, so the car inside uh, it's very hot. And well, what's gonna happen? Well, before you turn on the car, you gotta put on your seat belts. It's very important, guys. You gotta think about safety. So let's imagine that you put on your safety belt, your seat belt, and you make a mistake. That mistake right there. Have you done that before? Have you felt it before? You place your hand on the seat belt thing that you have there. I don't know what they call it, the buckle, I guess, and you put your hand exactly where the metal part is. You know what's gonna happen? That's gonna hurt you when you touch the metal, and it's gonna hurt you a lot. But if you keep your hands on the plastic part, you don't feel that much heat. You don't feel burnt that much, maybe. And why is that? Well, the idea is that, well, both of those materials received the same amount of heat from the sun and the atmosphere. They got the same energy, but they have different temperatures. Why is that? Well, it's because each substance, the plastic, has a different property than the steel's property to retain or increase in temperature, uh, given by an amount of mass that you have there. So each substance has its own number that can tell you how much heat is needed to change its temperature. So let's say, for example, the plastic depends on what plastic you have, but let's imagine that uh, it's made of this plastic, and it's going to be 1670 joules per kilogram degrees Celsius. That's going to be the specific heat for the plastic. And the steel specific heat, it's going to be 497. Well, this means that in order to increase the temperature of the plastic, you need more energy than the energy that you need to increase the temperature of the steel. That's what this number tells you. So the plastic requires more energy in order to get hotter than what you have on the steel. So the steel is going to increase in temperature faster or more than what you have in the plastic for a same amount of mass. Okay, so that specific heat, we can understand it in the following way. Okay, so this is what I'm telling you right now. It's you need more energy to increase the plastic temperature, and you also need you need less energy to increase the temperature of the steel. All right, that's what I'm saying right now. And specific heat is going to be a term that we need to understand because we're going to be talking about that a lot. So we're going to get into that, but let me just summarize this again. The heat that is required to increase the temperature of the plastic, you see this number, it's bigger. You need more heat to increase its temperature, but you see the steel, it's less than this one, so you need less energy. That's why heat is going to be, that's why steel or a metal, it's going to be uh, heated up more than other materials. That's why we make pans of metal, and the part where you put your hand to grab the pan, it's made up of plastic because the specific heat of plastic is greater than the specific heat of a metal. But let's continue over here. All right, specific heat, the symbol for that is going to be the symbol C, or the letter C, lowercase c. Alrighty, capital K C is going to be Celsius, and also some other thing called heat capacity, but I'm not going to tell you about that right now. I'm just going to talk about specific heat. Okay, so specific heat is going to be how much energy in joules, okay, how much energy, for example, that you can get from fire or from a fireball or whatever this is. And it's going to be how much energy is required to increase 1 degree Celsius of temperature, or in temperature, to increase by 1 degree Celsius 1 kilogram of a given substance. Alright, so this is like a density thing, kind of thing. If you remember density was something that is relative to each material, each substance, and this specific heat is also relative to each substance. Some substances need more energy in order to increase its temperature than others, and that's what that number tells you. But it's going to be for just 1 kilogram, how much energy you're going to be needing to increase its temperature by 1 degree Celsius. That's the idea of specific heat. So that specific heat is going to be specific to each material. Alright, let's continue over here. Also, how much energy is required, it's going to depend on what temperature you want to achieve. So for example, if you want to get a low temperature, you don't need so much so much energy. If you want to make a small change, you don't need so much energy. But if you want to make a bigger change, well, a bigger change in temperature, well, you'll need more energy. And all of this information that I just told you is going to be summarized in the following equation, which is right there. This is going to be the heat equation we will be using in the following problems. And the variables that we have here, you see that Q? That's heat energy. It's going to be measured in joules, the same joules that we used back then when we were talking about regular energy. That joules appears once more. It's just energy, heat energy. It's interchangeable. Anyways, let's continue. We have here equals the heat, which is Q, equals mass. That has to be in kilograms. If I give you something in the problems in grams, you bet you know what to do. You gotta change it to kilograms. And that C, that's gonna be specific heat, has to be in this unit. I didn't tell you before the unit. Maybe I did. I don't think I did. But now I'm telling you, the specific heat unit is going to be joules over kilogram times degrees Celsius. And this delta T appears again, and that's going to be the change of temperature, and it has to be in degrees Celsius. That's going to be your equation. Now, this equation can also be placed in the following way, because many times it will be very useful. They will tell you in the problem the initial temperature and the final temperature, the substance, which you have to look up in at the back of your book. There's a table there of specific heats, and you also have the mass. So many times they're going to tell you this information, and it's very useful to have this equation because it's ready for that type of problem, which are very usual. But now, guys, we are going to go into Physics Town. Now, today in Physics Town, we're going to be making some pizza in the pizza place. Well, we have here our ingredients. We got our bread dough, which is this. The bread dough has an average, a specific heat of 1,700 joules per kilogram degrees Celsius. And we're going to have for this pizza 1.5 kilograms of dough. We also have our cheese, which has this amount of specific heat. And it's going to have we're just going to use 200 grams of cheese. And pepperoni, we're going to use 900 grams. We're going to use a lot of pepperoni. And, well, it depends on what pizza. This is my pizza. I like pepperoni. I'm going to put more pepperoni than cheese. Anyways, each pepperoni, or the pepperoni substance, which is meat, it's going to be 1,470 joules per kilogram Celsius. And we're going to do 900 grams. And the tomato sauce, it's going to be 3,750 joules per kilogram degrees Celsius. And they were placed on inside a refrigerator, and all of them, they have the same temperature of 15 degrees Celsius. They all have exactly the same temperature. Alrighty, so something that we can mention here is that the tomato sauce and the cheese have the highest of the specific heats. That's very important, guys, because if you remember from your biology classes, tomatoes, or whatever from regular life or from your experiences, tomato sauce, it's made up pretty much of water. Water has one of the highest specific heats, which is 4,800 joules per kilogram Celsius. That's very high. So water has one of the greatest specific heats, and that's why the tomato sauce has a great specific heat, because it's made up mostly of water. But the pepperoni doesn't have so much water, as well as the dough. They don't have so much water as the cheese or the tomato sauce. This cheese is pretty fresh. That's why it has such a high specific heat. Anyways, we're gonna put this into the oven. We're gonna get that ready. We're gonna put that inside. We're gonna see what's the final temperature of our pizza ingredients. So what's gonna be the final temperature for each ingredient if the energy of the oven that we apply to the pizza is going to be 60,000 joules? What's going to be the change of temperature, and then what's going to be the final temperature? That's what we're looking for. And we're going to start with this equation. This equation is the one that I gave you, but we're going to clear for delta T. So delta T is going to be Q divided by mass times specific heat. This is multiplying these two terms, multiply these two factors, multiply, so you got to pass them as a division. You got to divide both parts of your equation by m times c. So you get this equation, which we will be using for each of the ingredients. Alrighty, so I'm going to use that equation, for example, to get the change of the temperature for the bread, for the dough. And the energy is going to be 60,000 joules. The energy is going to be the same for all of the cases because the whole pizza is inside the same oven. They all receive the same amount of energy, but you're going to see that each of them are going to change its temperature, their temperature, according to their amount of mass and also according to their specific heat. So this one has 23 degrees Celsius. That's going to be the change in the pizza dough, in the bread dough. Let's go with the cheese. Now this cheese, I told you that it was 200 grams. But in the equation, I can't place it as 200 grams. It has to be in kilograms. So I changed it into kilograms. And you know why we do that? It's because the specific heat that I gave you, it's in joules per kilogram degrees Celsius. So it has to be in that same unit in order for this equation to make sense. So we got, for the cheese, 81 degrees Celsius. Now let's do the same thing for the pepperoni, and we got 45.35 degrees Celsius. I told you that we got 900 grams, which is changed here in kilograms, and we got this amount in degrees Celsius. That's going to be the pepperoni. Now let's go with the tomato sauce. It gave us 94.1 degrees Celsius. That's going to be the amount of change in temperature for the tomato sauce. Now the question that they are asking us is, what is the final temperatures? What is the final temperature of our pizza, of each ingredient? So as you can see here, the dough has 47 degrees Celsius, and the tomato sauce is the highest, and the cheese is going to be almost as high. How do we get these results? Okay, before I continue, well, it's based on this equation. Remember delta T equals Tf minus Ti? The change of temperature is the final temperature minus the initial temperature. So I got it clear for Tf. This Ti is being subtracted, so that means that I got to do addition both parts in order for this to cancel and to get this equation. So we get the change of temperature plus the initial temperature, which makes a lot of sense, right? You start off with something and then you got to add the change. That's going to be the final temperature, and that's the equation that we will use to get the final temperature. In the previous steps, we calculated the change of temperature, and now which are going to be changing according to each material and amount for the dough, for example, but the initial temperature was exactly the same. Oh, okay, I used 24 here. Um, it's all right. I used 24. I used 15 previously, but okay, it's all good. Let's imagine that we started off with 24 degrees Celsius, a good ambient temperature, not very cool from the freezer. It's an ambient temperature, 24 degrees Celsius. It's pretty comfortable actually to be at 24 degrees Celsius. Anyways, 24 degrees Celsius is going to be the initial temperature for each substance, and then we are going to add the change of temperature due to the oven, and we got 47 degrees Celsius on the dough, and the cheese and the tomato sauce were the highest. That means, guys, that means that when you eat pizza, you gotta be careful. You gotta be careful when it's a very hot pizza. You gotta be careful more with the cheese and the tomato sauce, because that's what's probably gonna be burning your mouth more than the dough or the pepperoni. Okay, so that means that when you get your hot pizza, the cheese and the tomato sauce are hotter than the other ingredients, even though they were placed on the same oven. Now that's physics, guys. That's the reason why you get burnt by the cheese or the tomato sauce when you eat your pizza. You don't get burnt so much by the dough, you get burnt by the cheese and the tomato sauce. Why? Because they have a very high specific heat. That is the reason, guys. And why they have such a high specific heat? It's because they are made up of water, which has a very high specific heat. And we'll be talking about water later on because it's very important, guys. But that's it for today, and I wish you guys to have a great day.